So welcome everybody. I'm giving a presentation here on joint work that I co-supervise. The student is Fancy and is co-supervised by Martin Müller and myself. This is actually a short paper in the proceedings, so I'm doubly delighted that it was chosen for the joint session, but it really has just a single insight or observation in it, but I think it's an observation that you'll find useful if you do anything at all with global best first search, which is what GBFS stands for. The color's not coming out too good, but luckily the part you can't see is the part that doesn't matter. This is just a little slide depicting greedy best first search. It's a best first search algorithm which is driven by heuristic values with no regard for the distance from the start state. So the blue triangle that you can't see is the closed list, and then there's an open list which luckily shows up, and that's ordered just according to the heuristic that you're using. We had a paper last year at 2014 AAAI that extended global best first search in a simple way, which is depicted here by the red triangles, and that was that every now and then the global the GBFS looks like it's stalled, and we would detect that and do what we call a local search from points that were somewhat arbitrarily chosen from the open list, and we just do a little exploration forward from those searches to hope we can kind of unstall the GBFS. Now, I'm calling it now the global GBFS because, in fact, one of the methods that we used for doing the local search was also a GBFS. And so it's very important in your mind to keep track of the fact that there's the big GBFS that's stalled, and then these little GBFSs which launch themselves from a single node in the open list, and they keep their own private open list while they're doing that, so it stays small and focused. So that's what the red triangles represent here. And it turned out that this worked really well. So this is a slide from the AAAI 2014, and this is the typical slide everybody's showing these days, where you have time. In this case, it's time of one of the systems. In this case, GBFS without the local search is on the x-axis. GBFS with the local search is on the y-axis, and they're log-log plots. Each one of those instances is an IPC instance, which was run obviously by both systems, and you can just see how much time it took for each one. And as always with these pictures, which everybody is using these days, in our case, if you're below the diagonal, then then the local search is speeding up the GBFS, the global one. We like to put reference lines on these because it's a log-log plot, they're straight lines. So if you're below the 2x line there, that means that the local search is making things at least twice as fast. If you're below the 10x line, then you're getting a whole order of magnitude speed up. And if you're below the 50x reference line. So you'll see those reference lines on all the slides that I show like this, just to give you some sense that there is some very big wins happening here. So that was that was what we did in reporting in 2014, but we didn't have a good explanation for what was going on. And that's the contribution that we made here in this short paper, is we have at least one explanation which applies in quite a few of these instances where we got the big win. And I'm just going to illustrate, to start telling you what the insight was, I'm going to focus in on a single IPC instance. This is from the 2004 no tankage competition, and this is instance number 21. Jörg Hoffman did an analysis of these domains a few years ago, and he showed that in this no tankage domain there are no dead-end states, so that's not causing the problem. But what there are is unbounded, what we call uninformative heuristic regions. Some people call them local minima, some people call them plateaus. We give this big long name so that we can have a short acronym, and we now call them UHRs. So this is going to be the focus of the explanation that we're going to give, is that these unbounded UHRs are what's causing the trouble. So here is just what have we got on this plot. It's kind of funny because 0 is on the right, it's not on the left, and this is because as time passes, the smallest heuristic value on the open list decreases. So in some sense what's happening is time is passing as we go from left to right. Here you start with a high minimum heuristic value on the open list, and it gets smaller as time goes on. And the total time taken to achieve till the first moment when you have the smallest heuristic value of x is what's shown on the y-axis here. And so you can see that the red line is the GBFS by itself, and GBFS with local search is the black dotted line there. And you can see that everything goes along swimmingly until you hit the value 6. And then at this point, with the local search, you very quickly move on to 4, and then to 2, and then to 0, and you've got the goal, whereas this is a point where the global GBFS is getting stuck. And because this is a logarithmic scale on the y-axis, what looks like a fairly small jump is actually a huge jump, and in particular, it takes about 1,000 seconds for GBFS to do these 2 reductions, the 2 that you can see from 6 to 4 and from 2 to 1, whereas GBFS with the local search solves the whole problem in 2 seconds. So here is the big insight. If you want to remember one slide from this talk, actually it's not this one, it's the next one. But anyway, this is a good warm-up for the next one, because the next one's a variation on this. So you've got the closed list, you've got your open list, and then way down there at the bottom you've got your goal states, which you'd like to get to. And what's going to be the cause of the problem is you have this large plateau, local minima. We call it a virtual UHR. And the word virtual here is really key, but I'm not going to explain it to you. I'm going to let you guess what it means for a while, and then I'll tell you in a few minutes what exactly it means. But what this is it's a part of the space where when you expand somebody in the open list, you get somebody with the same heuristic value. So I'm using the heuristic value 2 here, because this is actually sort of representative of what we saw in the previous slide. And then maybe you would expand that one, and you get another one with 2. So you get this big set of nodes that are all connected to your open list right now, which all have the same heuristic value. So that, like I said, lots of people call this a plateau. The thing that then causes the problem, if you just had a big plateau, well, you might just go zooming through it with a depth first kind of a flavor, and so you wouldn't have any trouble. But imagine that every one of those paths that leads you from your current open list towards a goal state eventually hits a node with an H value of 3. Now, greedy best first search is greedy, so that's going to be considered a stopping point for the moment until it has flushed out all of and even generated that whole virtual UHR. So if you have a complete barrier so that you can't get to the goal nodes without going through a barrier from your current open list, then this is what we mean by a virtual UHR blocked by a barrier. The nodes just beyond the barrier are ones that have got smaller heuristic values, so they represent progress finally. So if you can get through the barrier, you'll get to some progress nodes. So this is the total picture that was our insight of what was going wrong with GBFS. But this doesn't explain why local search caused an improvement. It looks like local search would also bump into these barrier nodes, and life would just be bad for everybody. So the question now is, given that this is what we think is going on, what's the explanation for why local search would help in this situation? So I'm going to focus in on 2 nodes that are on the open list. Of course, this is all just a cartoon, but 2 nodes that are on the open list. There's the one on the left and the one on the right, and I use the same color scheme here. So you can, if you look at just one side of this picture, you'll see the same structure we saw in the previous slide. You'll see there's an open node, and then all its descendants that have a value of 2 are in that gray color. Then there's the barrier nodes, and then the escape nodes at the bottom, and the goal nodes down below that. So this is the composition of that large virtual UHR is actually made up of a whole bunch of little separate UHRs. And these aren't virtual anymore. These are really, you can really get from that open node to all those descendants, but you can't get from the guy on the left to all those descendants on the right. It's just not, it's not a connected region. So when you think of it as a plateau, you're at least my imagination is always that it's a connected region, but it's not. It's a gigantic union of a bunch of smaller regions. And this is now this is the observation that then allows us to explain why local search is helping in many of these instances. So this is what we call a large local UHR. There's many nodes. It's really got the same problem that GBFS has, is there's just way too many of those nodes, the descendants with H equal to 2, followed by a barrier for local search to do any good. So that one, it wouldn't, local search is just going to be stuck like everybody else. This is the one that's important. This is the reason that local search can get you out of a large virtual UHR with very little work, is because it could be a small local UHR. Small means that you only have to expand a very small number of nodes before you not only hit the barrier node, but you get past it. Because you have a budget, that I forgot to mention that on the slide, but local search is given a budget of, you can do, let's say, 1,000 node expansions, which is the number we used last year. So it will get past this. It only needs 4 nodes to escape this, and if it's allowed to do 1,000, it'll get way past this. It'll hit the escape node, and that escape node will then, even if it didn't go any further, would get put on the global open list, and then the whole global search would now have a heuristic value of 1 and could proceed from there. So this is the key, is that the large virtual UHR is made up of a bunch of actual UHRs, some of which might be so small that you can just blast through them. And that's what the local search does. So a key acronym that you need to get used to in this talk, and I only have 7 minutes left, but for these next 7 minutes you need to understand what an NEE is. So in this example, I told you need to expand 4 nodes in order to escape this local UHR. And so that means that this UHR has an NEE of 4. And we actually associate that with the node on the open list. So the node at the top of this picture, we would say that that node had an NEE of 4. So that's the key concept that we're now going to look at, that we're going to sort of pin our explanations on. So local exploration will help GBFS if there's a large virtual UHR with a barrier, as I showed you on that one picture, and it contains a sufficient number of small local UHRs. So, and these things are in red because what do they mean? Well, let's just go back to that no tankage instance number 21, and we took a snapshot of the open list when it had about 5,000 elements on it, and all with h equal to 2. And we asked ourselves, we just computed for every one of the nodes on the open list, what is its NEE value? And then we put them in, as you can see, we put them in these logarithmic buckets. Some of them, like the one I showed you, although that was a cartoon, it wasn't a real example, some of them had an NEE less than 10. Some of them had an NEE between 10 and 100. In fact, you can see the exact number over there. There's actually 456 nodes out of the about 6,000 that we looked at when I was these numbers, that had an NEE that was tiny, between 1 and 10. There was another 66 that were between 10 and 100. Oddly enough, there were none between 100 and 1,000. So you either have a small one or a big one. In this particular instance, there was no middle ground. You either have very small or you're very big. So the majority, it's true, the majority are bigger than 1,000, but we don't need them all to be small. We just need to be really, we just need there to be one small one, but then we have to be able to find it. Because we're going to be randomly sampling, what we need is more than one. We need some reasonable percentage. And so you can see there the percentage is written down. There's about 8% of the nodes have got these very small UHRs, NEE, sorry. I'm now going to show you a different kind of plot, just in case you're curious about how things happen. And so if you plot NEE on the x-axis, and you ask yourself what percentage of the nodes, what percentage of the nodes have an NEE value less than or equal to an x value, then you get a curve that looks like, obviously this ultimately goes up to 1.0, but we didn't look that far because we cut things off checking for 1,000. And so again, so last time we saw that about 7% of them had an NE value of 10 or less. And so that means on this plot, at x equals 10, it would be up around 7%. I drew a horizontal line at 5% because we're kind of considering that a sufficient number. So here it is, in case you're wondering if it only happened on that one instance and no tankage, we checked out all the other domains, and we didn't check all the instances because we had about 2,100 instances, but we just checked each domain to see if there was one instance in those domains. And so if you can read the print, you can see the domains that where we found these small UHRs. And then this is the same plot I showed you before, but with all those domains on there. And so you can see where they cross the 5% line, which is that dark black horizontal line. You can see that there's a lot of variation. But the main point is that an awful lot of them cross around 100 before, with x equals 100 or less. So then this leads to an idea of how to improve the paper we reported last year. It's a very simple idea once you have this insight. In 2014, the GBFS LS did one local search. It's almost like Yenrik doing one, we did one local search and expanded 1,000 nodes. But now we know that 1,000 is actually not a good cutoff point. Having looked at those numbers, we know that we would actually, the NE analysis I just showed you, say it's really kind of a waste to expand 1,000 because after 100, there's basically nothing. And so you would be a lot better doing more searches, but giving each search a smaller budget of nodes to expand. And so that's what we report in this paper, is we looked at various values of M and N. So we're going to try M local searches. When the GBFS globally stalls, we're going to do not just one search with 1,000 nodes, we're going to do M nodes with a budget of N, where M times N equals 1,000. So the total number of nodes expanded in this exploration phase is still 1,000. And we're going to choose the nodes at random, which is not what we did in 2014. So we have this little notation down here, GBFS LS -10x100 means we're going to do 10 searches, and each one will have a budget of 100 nodes to expand. So now this is a comparison slide again, similar to the one we saw before, except now GBFS LS from 2014 is on the x-axis, and GBFS LS with the 10 by 1,000 instead of the 10 by 100 instead of the 1 by 1,000 is on the y-axis, and you can see that there has been some slowdowns, but there's been lots of improvements and some very big improvements. All of these experiments were done using the FF heuristic, and some of you might say, well, that's a lousy heuristic. Who would ever use that heuristic? And maybe you only get plateaus if you use the FF heuristic. So we also looked at the causal graph heuristic, and this is the same thing. This is GBFS LS from 2014 on the x-axis and the time for the 10 by 100 version of it. And again, you see lots of stuff below the diagonal, which means that, again, there's lots of small UHRs, even if you're using the causal graph heuristic. And the same is true if you're using the context enhanced additive heuristic. So it could be specific to the heuristic you're using, but these are three of the popular heuristics in the planning literature, and you get pretty much the same picture in all of them. So that's the end of it. I think I've pretty much hit my time here. So the question we were asking is, why did the local searches improve a greedy best first search? And the answer is that the plateaus and the local minima that you're running into with the global GBFS are actually made up of a whole bunch of UHRs. It's the union of them all, and some of them are small. A non-negligible fraction are small in many of the domains. And that's all I have to say. Thank you very much.